Hello and welcome to what's going to turn out to be Plate Tectonic 3. We're going to start talking about the three types of plate boundaries. Earthquakes, we used to call this tension, and if you look at all three of these have arrows pointing in different directions. These are pointing opposed from each other. These are pointing toward each other, and these are actually moving in opposite directions from both sides. We used to call this tension. We're now going to call it divergent, which means moving apart. We called this compression with earthquakes. We're going to call that convergent, moving together, and we called this a shearing force. We're going to call that transform. And these are the three ways that plates interact. They all produce shaking, some of them more than others. Two of them produce really good volcanism. One of them better than others, or better when I'm saying is more violent. The much more explosive volcanoes, which I think tend to be much prettier to watch than the things that just throw molten rock up in the air and you can sit there in bleachers and watch it. So what I'm going to do first is I'm going to show you this shockwave file, and I think you can see the whole URL, but if you just type in plate motion SWF, you can see this, and this actually shows you divergent plates. And if you take a look, you can see these plates are actually diverging. You can see the key up there shows you earthquakes. All the earthquakes happen very shallow, and they happen in a nice straight line. This line happens to be about 46,000 miles long. It makes the mid-ocean ridge, those ridges you see in maps on the ocean, which I'll show you later. But as you can see, you get molten rock rising, and it actually moves like a conveyor belt, and it splits these two plates apart. It diverges the plates, and it produces an upward push, which is the ridge. They tend to be in the middle of oceans, which is why they get the name. The nice red color there, we have nice mafic, which is magnesium iron rich molten rock coming out of the mantle, coming up to the surface and creating an ocean floor, which is what this is showing you. This is in the ocean. A place where this actually does stick up is Iceland, probably a hot spot and a mid-ocean ridge at the same point, where we have a lot more molten rock coming out than normal, and it actually is enough to make an island that focuses and points up out of the Atlantic Ocean. And if you watch that, you can see it move over and over and over, and it just keeps doing this, and the Atlantic Ocean's been doing it for the last like 250 million years. Divergent, this is going to be an oceanic crust again with an oceanic crust, and we get these two mafic um, plates actually hitting each other. One of them, which could be the thinner, but could be the older, but one of them actually subducts down under. Subduct means to push under, and when it comes down here, it melts. It produces mafic type material, which can actually move up and with a couple of different processes, dehydration and some other things that can produce some more felsic type of material, although it's still going to be mostly mafic. This one, where the other one produces molten rock, not so many volcanoes, this one produces volcanoes, some of which can rise up out of the surface. Some of them can get quite large, like the Philippines and Japan and the Aleutian Islands. We'll call those mature island arcs. If you take a look, the arrows are coming toward each other. You get earthquakes at all kinds of different levels, although they spread out. You're probably going to get shallow earthquakes all over this area because this rock does not like to be pushed up and ground into it. You're going to get some medium or intermediate, and you're going to get some really deep type earthquakes in this type of convergence, where the divergent was all shallow, all in a line. These are going to be all three types of shallow, intermediate, deep, but spread out a little farther. And the transform faults work like this. And if you take a look, you move and you get earthquakes. Again, these are going to be in a linear fashion because this fault is straight up and down. If this is continental crust, it tends to be a little thicker, and you can start getting intermediate and maybe some deep earthquakes, but again, they're going to be right on top of each other rather than spread out like they were in this one. And in this one, a nice linear form. And if you throw them all together, you get divergent, so you get convergence, and where this mid-ocean ridge offsets. And if you've ever tried to break an egg or peel an orange, it does not break in a nice smooth line. The Earth is like those in terms of geometric shape. So we actually get these offsets, and in between this ridge and that ridge, we actually get plates moving one to the left and one to the right. We get a shifting force in there, and you can see as they diverge, and again, shallow earthquakes all along this line. We may get some deeper earthquakes along this, especially if it happens like in California with the San Andreas Fault. And here we're going to get mafic going underneath continental, and as it rises, we're going to get differential heating and dehydration, where we're going to actually get mafic turning into felsic, and we can get felsic and we can get the composite cones out of this rather than maybe just shield or cinder. And if you take a look, they're showing you ages, so this doesn't happen over a day. If you go through this whole thing, it's 100,000 years. Okay, can I minimize this one? Let's go back to this. The first one I want to talk about is Divergent. Divergent is just going to talk about this area right here. These are spreading centers. They're also called mid-ocean ridges, or what I call MORs. They're rift zones. They're spreading ridges, spreading centers. And basically what happens is you get these convective cells opening up in the mantle, and it comes up, it diverges, and it will pull the plates like a conveyor belt, allowing mafic rock to come up. It's a nice cool ocean. They solidify fairly quickly, and it's where you can find new rock almost every single day of the year. I do want to show you this one too. This is going to tend up to be a long video. Okay, this is if you type Divergent SWF, and this is continental, then you have lithosphere. This is what makes up the lithospheric plates. And then you have the asthenosphere. And if you take a look at it, the molten rock rises. It diverges the lithosphere mantle, makes it thinner. You can see it's actually causing, and this is a hanging wall, and the hanging wall slips down. It's actually causing normal faulting, and it shows over a large area, and eventually one of those will win, and it's the one where the molten rock starts coming up. And we start getting sedimentation because we're going to get weathering and erosion, and the weathering brings the rock down into the valleys. We start getting sedimentation. The Rift Valley is there. We have volcanic activity. Primarily it's going to be felsic for a while, then it's going to start being mafic. An ocean's going to start forming. There's the ocean, and we have a linear ocean, maybe a mid-continental ocean, and as it gets wider and wider, we start getting a bigger and bigger ocean, and we have the birth of the Atlantic Ocean like 250 million years ago. Age of the ocean floor, if you take a look at these ages, we have 100-million-year-old rock being in the blue. I think it actually gets a little older. Those tend to actually be by the convergent areas. The red areas are the divergent areas. There's the mid-ocean ridge, and there's Iceland, which is probably, like I said, a hot spot and a divergent area at the same time. You can see that they go all over. The reason this is a much wider, this is called the mid-ocean ridge. This is called a mid-ocean rise. This tends to spread a lot faster. It's one of the fastest divergent areas on the planet, where these can go about the speed of a fingernail. This can go 4 or 5 times that rate, 3 centimeters per year, and maybe even 17s and 20 centimeters per year, so it can go a lot faster. That tend to make something that's not quite as tall and much more wide, not as steeply sloped as this side, but basically mid-ocean ridges are where you find the brand new baby rock, and as far away as you can get to it, that's where you find the oldest rock. Iceland's a really good example of continental rifting, where we actually have a landmass that's being pulled apart. There's lots of normal faulting going on here, lots of mafic rock, but the molten rock tends to come up out of these volcanoes very frequently. They open up fissure flows, which are big cracks in the ground, and molten rock comes out. It is mafic in consistency. It's not very violent. It shoots up in the air, especially at night. You can see the yellows and the oranges pop up, and you can see the reds roll around. It does form solid fairly quickly, at least geologic time. You may have to wait a few weeks or years if you wanted to walk on it, but you can walk on Iceland, parts of Iceland that are a year old. This is actually an island off the coast, way down right about here, that actually in the 1970s opened up a fissure and threatened to close down the fishing harbor here, and they took seawater and sprayed it on there to stop the molten rock. Not much you can do with it, but for the one time, they actually did a fairly good job of stopping it. Convergent boundaries, these are where they come together. These boundaries come in 3 styles. They come in oceanic convergence, they come in oceanic continental convergence, and they come in continental convergence. And this is not the most current PowerPoint that I have. I can tell because there's a missing diagram, and I can also tell that the mid-ocean ridge and deep ocean trenches here are not in red. Oceanic collision or convergence is when we have 2 oceanic plates. One of them rides into the other. It causes it to sink. It is subducted down. It's called a subduction zone, forced down under zone. These subducting plates bend, and as you take a look at this subducting oceanic plate goes down. It produces shallow earthquakes all along this surface and produces intermediate earthquakes and deep earthquakes as this rock is pushed down into the mantle. It really wants to be at the surface. It's heated up, it melts, it actually goes through, and if it comes through enough, we'll actually get these volcanoes. They can be called seamounts if they're underneath the surface of the ocean, and they can be called guyots if they used to be islands and they erode back down, or they can be called islands. We normally call them a volcanic arc or an island arc. It does make a super huge, super deep trench where we actually have the deepest depths in any ocean. The Mariana Trench is the deepest place, 11 kilometers, about 36,000 feet deep. Very deep, high pressure, and a place where lots of really funky critters live. Speaking of the critters, we have lanternfish, and we have anglerfish, fishes that fish for fish, but they all have a really weird shape to it. They don't live very long at the surface because they're used to such deep depths and high pressure. Pretty much the only way we can see them is to send submersibles. We've had a couple of manned submersibles go down into what's called the Challenger Deep, and most of the time it's unmanned. It doesn't have to be as big, doesn't have to carry water, doesn't have to be heated, doesn't have to have a whole lot of things that we require. Continental oceanic is when you actually get an oceanic crust running into continental. Continental is felsic and more buoyant. Oceanic is mafic and more dense. It always takes the dive. It is subducted again. It comes down, the mafic material melts. You get partial melting. Felsic rock tends to have a lower melting point, so it melts and produces the lavas before the mafic stuff does. So we tend to actually get a composite cone with mafic and felsic lava flows for this type. These are called volcanic arcs, where they're called island arcs when they're oceanic. Subduction, oceanic lithosphere subducts underneath continental. Again, we're going to get shallow, intermediate, and deep. We're going to get partial melting. We're going to get these really beautiful composite cones where we get felsic displays and mafic displays. It actually is going to have this dehydration. Dehydration lowers the temperature, which actually makes the magmas become more felsic. And a real good example of this is the Andes. Then we have continental. Continental, this is where two continental plates run. The real good example of this one is the European Alps or the Himalayas, where we actually have two continental plates. Neither one of them wants to be subducted, so what happens, it tends to be just like a train wreck, and it actually makes a really mountainous area. Himalayas are the highest average plateau any place on the planet, and if I showed you what one of those looks like, this is going to be the Indian landmass, which is on the Indo-Australian plate, which is moving away from this divergent area. And starts way down here. And 71 million years ago, it actually starts finding its way north. It's running through a whole lot of marine sediments, and it's pushing those up. There's 55 million years ago. And then right around here, it's taking all this oceanic rock and it's pushing it up into the air, and this is why you can find marine fossils on top of the Himalayas. But it pushes up and makes the highest average elevation any place on the planet. Example again is the Himalayas, and that happened when India moved up and slammed into the Eurasian plate and produced really high mountains, snow all the time, highest elevation on the planet. It does have volcanism for a while, so we do have volcanoes in like Tibet, but as soon as this continental landmass runs into this continental, the subducting ocean floor is cut off, and then basically it's just like one continent running into the next, which is pushing up the Himalayas higher and higher every day. The last thing we got to talk about is transform boundaries. This is when we sideswipe, and you can get shallow earthquakes in here, and you can get intermediate earthquakes and deep earthquakes, but they tend to be all in a straight line. A real good example of that is the San Andreas Fault, where we get mountain ranges. It does deform. Another good example is where the mid-ocean ridges are offset, the areas in between, like that right there. So anywhere on the mid-ocean ridge, anywhere San Andreas Fault, which is a very large faulting area, transformed fault area, that's now actually being exposed at the surface of a continent as North America is moving over the Pacific plate. And basically everything on this side is Pacific, and everything on this side is North American plate, and that's the fault that actually separates the two. Plate boundaries, if we start looking at all the divergent areas, which are the thin lines, and the convergent areas, which are the thicker lines with the teeth, much more violent, large earthquakes, lots of volcanism, we start actually seeing the plates. And again, the plates take the name of usually the landmass, except for the Pacific Ocean. It takes the name of the landmass. I'm not sure exactly why this is called the Cocos Plate. I don't know why this is called the Nazca Plate. But it's pretty easy to see Antarctic, South American, African, Eurasian, North American, Philippine plate, excuse me, the Indo-Australian plate, which is right there, which is moving away. So Australia is moving up, and that's why this plate is being subducted underneath. And these arrows actually showing you that this is the plate that's dying. The earthquake that we actually had just a week and a half ago up here in Nepal is caused by this Indian plate slamming up into this Indonesian plate. Speed of the plates, like I said, over here it can be in double digits. The Atlantic Ocean pretty much fingernail speed, 2 to 3 centimeters. That's a centimeter and a half this way and a centimeter and a half that way. So the two land masses are separating by 3. Just like this 17, it's half of that speed maybe this way and half of that going this way. That's pushing the Nazca plate underneath this oceanic plate underneath this continental plate. The Juan de Fuca plate, which you see very little in this picture, is almost completely inundated by this North American plate, and that's the reason why this San Andreas Fault, which is just like one of these little strait areas, now is actually on North America because the North American plate's pushed over. The Pacific plate's dying underneath there, it's dying underneath there, it's dying there, it's dying there, and this is why we call this the Ring of Fire, because we basically have volcanoes up the middle. We have volcanoes in South America as that Nazca plate dies, which is the Pacific Ocean. North America, Central America, the Aleutian Peninsula, this island arc, which is up here, a mature island arc, which is up here in the Russia, Japan, the Philippines, all these islands down here in Sumatra. Really good example was Kilauea, which is right about there. 1883 exploded. Nice, beautiful composite cone. But you can see some of these areas are really small, like you see up here. And part of that has to do with the fact that this one is really high up in the earth. And then how far will USA be from its present position? If it's 1,000 years, they're going 3 centimeters per year away from Asia. You'd actually expect to multiply this number by 3, and that number by 3, and that number by 3, and you can come up with a relatively easy answer. Okay, I think that's it for Plate Tectonics 3. Appreciate you stopping by. Hope you took good notes, because you know I will be checking.